Rules of inference. There you are again. This is week 4. It's actually the 5th week of the semester, but it's the 4th unit of logic in our semester. And now we are embarking on the second method for testing an argument for validity. This is the method we're beginning to use real proofs now. And this is the method that uses rules of inference. Okay, it can work entirely on its own, although it works best when conjoined with the replacement rules that we'll be doing next week and that your textbook explains in Unit 8. Okay, that's replacement rules. But replacement rules are ancillary, really, to the rules that make a proof function, and those are the rules of inference. I don't like to use metaphors that are too forceful, too ferocious for arriving at validity in an inference. I also don't like to use mechanical metaphors because those are just false. For all the tedium in a truth table, it had the advantage that it could work as an algorithm. It could be seen as a machine. You put the formula in, you grind out the truth values, and by a clear rule that never goes wrong, that suffers no ambiguities, you can determine whether that argument is valid or invalid. Now, for several reasons that procedure does not apply to rules of inference, you're going to need indeed some ingenuity, some creativity as the proofs become harder. You have to see how to get to the conclusion. But as I said, I still don't like metaphors of force, aggression, victory, because after all, that's not what performing a proof feels like to me. To me, it feels like a walk that we take, starting with the premises, and if all goes well and we don't get lost, winding up at the conclusion. It's not, however, I must say, an adult way of walking. When you walk as an adult, you do something else, and then your feet just carry you along. So whereas a toddler has to be very analytic, and to get across the room has to think, okay, I can just make it over to the coffee table, I'll grab onto that, then over to the sofa, and so on. And in this way, it's called cruising when toddlers do it. In this way, cross the room. Okay, there's something like that going on in the rules of inference that we use to arrive at the desired conclusion. I hope you see what I mean as we proceed. The downside of what I mean by having to stop and think about what you're doing is that occasionally the rules of inference describe a step from point A to point B that is so obvious, trivial, indubitable that you almost can't see it. Okay, there I just ask you to be patient. We have to get used to spelling out even what we would think does not need spelling out. Okay, it's just a practice we have to get into so that proofs become more natural in the long run. To guide us on our walk from premises to conclusion, we have what our textbook identifies as the 8 fundamental rules of inference. There can be some modifications. Sometimes a larger set is used, sometimes a smaller, but these are more or less the 8 rules of inference that apply to any truth functional proof. Now, there are 2 general features that these rules of inference have. First of all, they're unidirectional. Okay, a proof does not move equivalently from premises to conclusion and then back from conclusion to premises. It's a one-way ticket. The conditional, the material conditional is a good example of how to think about this. If P then Q means something different from if Q then P. Okay, and so too with the rules of inference. They will show you how to get from premises to conclusion. You cannot use them to get from conclusion to premises. Second, and the import of this second rule might not be as clear until we have studied the replacement rules in the next chapter. A rule of inference applies to a structure that takes up an entire line of a proof. You cannot use a rule of inference on some subsection of a line, right? So if it's a rule of inference that proceeds from a conditional, from an if-then, okay, fine, well and good. But the entire line has to be, in some large sense, an if-then statement. If it's a rule of inference that applies to an or statement, a disjunction, it can be as complex a disjunction as you want, but the entire line has to be a disjunction. Take a look at these two sentences. If A or B, then C, and A or if B, then C. Now, you're sophisticated at this point. You know that these are two different statements. That's not the point. The point is that the rules of inference that would apply to this line are the rules of inference having to do with conditional statements, modus ponens, modus tollens, the hypothetical syllogism, dilemma. The rules of inference that apply to this line are the rules of inference applying to disjunctions, like disjunctive syllogism, okay? And in a different way, dilemma. It doesn't matter in that sense that there is a disjunction here. This is, how shall we say it, at heart, in its essence, well, for the purposes of inference, that is a conditional statement. And it doesn't matter here that one part of this disjunction is itself a conditional statement. This is, as a whole, understood as a line of the proof, it is a disjunction. And the rules of inference that apply to that line that can be used to draw further consequences from that line have to be the rules of inference applicable to disjunctions. All right, then, let's begin. And we won't forget to demarcate these rules with the abbreviations proper to them. You can see them in the textbook, and they tend to be pretty standard abbreviations, like MP for modus ponens, MT for modus tollens. You have to indicate the name of each rule at the end of the line in which you apply it in the syllogism, so that there's no ambiguity about what you're doing. in some versions of truth functional logic as a complete system that requires axioms, modus ponens is given as one of those axioms. You can do it without modus ponens, but modus ponens is standardly one of the axioms of truth functional logic, and that ought to indicate how important it is as a rule of inference. Modus ponens lets you get from any given conditional statement and the statement of its antecedent to the consequent. If A then B, A therefore B. It's an extremely fundamental rule. It's the way of affirming, modus ponens, the way of affirming, as modus tollens is the way of denying. If A then B, A therefore B. Now, this is so, I'm going to say something that sounds contradictory. It's not meant to. Modus ponens is so ingrained in our thinking and our use of if-then that people even misuse it and sometimes reason, if A then B, B therefore A. No, that's not modus ponens. That, indeed, it's so common, it has a name. It's the fallacy of affirming the consequent. It's still a fallacy, don't get me wrong. The fact that it has a name at least should reassure you, should you find yourself making this error, that you're not alone. It's a very common fallacy, okay? But we don't want to make that fallacy. We want to use modus ponens the right way. If A then B and A, therefore clearly B. Now, the accompanying rule of inference to modus ponens is modus tollens, abbreviated MT. If A then B, not B, the negation of B, therefore not A. This is different. We're not affirming the consequent, we're denying the consequent, and by denying the consequent, we are entitled to infer the denial of the antecedent. To use the example I'm so drawn to, if the car runs, there's gas in the tank, the car runs, there's gas in the tank, boy, doesn't that ring true, as opposed to that fallacy of affirming the consequent. If the car runs, there's gas in the tank, therefore the car runs. Well, no, that's clearly not going to work. Here, if the car runs, there's gas in the tank, there's no gas in the tank, therefore the car doesn't run. That makes sense too. The accompanying fallacy, and by the way, I realize you can take these fallacies and group them in the other way, this one with modus ponens, the other one with modus tollens. That doesn't matter, they're both fallacies. But what we call the fallacy of denying the antecedent, if A then B, not A, therefore not B. If the car runs, there's gas in the tank, the car doesn't run, therefore there's no gas in the tank. Well, that's an optimist for you. Didn't you know there are so many other ways that a car could fail to run? You can't conclude that there's no gas in the tank. All you know is that if it's running, why, yes, there's gas in the tank. I don't know why this next one feels the most obvious to me, certainly of all the rules of inference involving if-then statements, conditionals. If A then B, if B then C, therefore if A then C. If we're moving, then the car is running. If the car is running, then there's gas in the tank. Therefore, if we're moving, then there's gas in the tank. Doesn't seem to be much more you need to say about that. Okay. Now, and that's the hypothetical syllogism written HS, or named HS. Now we can already perform one simple derivation, one short proof. Suppose you're given these three premises: A, if A then B, and if B then C. Well, from lines 2 and 3, you can get if A then C, and here we write 2, 3, HS. And from lines 1 and 4, by modus ponens, we get C, the desired conclusion. Okay, so we can use modus ponens and hypothetical syllogism together. As there are three rules of inference exclusive to the material conditional, involving only the material conditional, so too there are two rules of inference exclusive to the conjunction. And by the way, you might think it's a contradiction when we've been showing all along that you could actually function without a material conditional, that you can always redefine a conditional in terms of a disjunction and a negation. You might say, why begin in our rules of inference with a conditional, with these three rules proper to the conditional? Doesn't that contradict what you were saying? On the contrary, what these rules of inference indicate is that we really need conditional statements for truth functional proofs, that capture what we try to do with everyday truth functional reasoning. The conditional is absolutely essential. It's so important indeed that that's why we have a special symbol for conditional, even though we could translate that conditional symbol into disjunction and negation. We could, but it's so useful on its own terms, just by itself as a conditional, that we take the trouble to add this, technically speaking, extraneous connective symbol. Okay. That's a little sermon on behalf of the material conditional. So as I said, we have three rules of inference specific to the conditional, and we have two rules of inference specific to conjunction. They are conjunction and simplification. In my experience, just so you know, conjunction is used much less frequently in proofs than simplification. Conjunction is one of those rules you can use when everything is lined up, when you've got both the A and the B, and you have a need for the two of them conjoined, you put them together. It happens. I'm just saying, from what I've seen of truth functional proofs I've done, it doesn't happen as often. I merely remind you something you've heard before, you'll hear again. The things that get conjoined don't have to be individual letters. We can have A or B, and if C, then D, and we can conclude A or B, and if C, then D. That's the same rule, conjunction. You take this whole line, you can't take part of a line. You take this whole line, you can't take part of a line. and you can join them. It's much easier to move in the opposite direction, and that is to take any part of a conjunction and assert it alone. If today is Wednesday and it's snowing, then it's true that today is Wednesday. When both things are true, one of them is true. If you're conjoining three statements, A and B and C, then you can state any one of them or any two of them, right? This is a good example of how rules of inference are one-way rules. They do not proceed in the opposite direction. To go from A and B to A is rationality itself. To see A and go to A and B, oh, you'll just get lost, right? Terrorized on that road. Don't do that. You cannot proceed in the opposite direction. Now, in disjunction land, on the other hand, you can proceed easily in the opposite direction. Okay. So often, disjunction does not behave as conjunction does, but there's a certain parallel, sometimes a certain kind of negation. Okay, so where you have A, you can infer A or B. Notice again, this is a one-way ticket. You can't go from A or B to A. The world would be very different, right? To conclude from the promise, tomorrow, either we're going to the dentist or to the zoo, you cannot conclude that we're going to the zoo. Right? The world would be a very different place. It may well end up that you go to the dentist. Okay, but from tomorrow we're going to the dentist, you could conclude, though it would be wishful thinking, that you're going to the dentist or to the zoo. The rule of addition is one of two rules specific to disjunction. Okay, remember we had the three rules specific to conditionals. We have the two rules specific to conjunction. The rule called conjunction, confusingly enough, and the rule simplification. Now, with disjunction alone, we have addition, whereby we take any statement and we get the disjunction of that statement and anything else. And we get the somewhat more complex but more interesting disjunctive syllogism. A or B, not A, therefore B. It's common sense. Well, of course it's common sense. These rules of inference are premised on the idea that any one of them by itself seems obvious, almost too obvious to state. And where logic gets interesting, where proofs get interesting, is in starting with these very obvious steps and then being able to draw inferences that were not as obvious when you started out. Okay. So the disjunctive syllogism tells you that if it's one or the other, and it's not one, it's going to be the other. Okay. And finally, we have the construction that our book calls a dilemma. It's commonly called a dilemma, but in some books, it is divided in two. There are two versions of it. I'll give you both of them. It doesn't matter if you treat them as a single rule or two versions of a rule or two different rules. That doesn't matter. This is the dilemma. You have to have two conditionals and a disjunction. And the disjunction is the disjunction of the antecedents of these two conditionals. If A, then B. If C, then D. Either A or C, therefore either B or D. So this conditional promises you that if you've got this antecedent, you get this conclusion, this consequence. This conditional promises you that if you have this antecedent, you get this consequence. And now this third premise tells you you've got one of the two antecedents. Therefore, by the rule dilemma, you've got one of the two consequences, okay? This disjunction kind of kicks it all in motion. It tells you, right, one of those two is going to come true. And so you can conclude that one of the two consequences similarly will come true. Now, as I said, our book treats this as a single rule called dilemma. You want to treat it as a single rule called dilemma? Fine. Nothing weird will happen. Okay. But sometimes it is referred to as the constructive dilemma, and it is twinned with, yeah, you guessed it, destructive dilemma. The destructive dilemma starts with the same two conditionals. If A, then B. If C, then D. But it says not B or not D and concludes not A or not C. In other words, it tells you one of those two consequences is false, right? It denies one of the two consequences. And so you know that therefore one of the two antecedents must be false. You don't know which one it is. It's going to be not A or not C. Okay. What does that look like? Well, that reminds you, of course, of modus tollens. The destructive dilemma is to the constructive dilemma what modus tollens is to modus ponens. Okay. Can you live a full and happy life without separating this into two rules, destructive dilemma, constructive dilemma? Of course you can. I just find sometimes it's easy to have both of them enunciated as clear principles. Not necessary. I'm just pointing out that these are the ways that we can reason. Now, some of the other material covered in this chapter on the rules of inference pertains to what we might think of as the etiquette, the traffic rules of logical proofs in truth functional logic. That means you can still get to the conclusion of a valid argument without these. You can still assure yourself that the argument is valid, understand why it's valid without these, but they simplify the practice of making clear what you're doing, both for yourself when you come back to understand it again, and for another person with whom you're trying to communicate. So these include such just simple procedures as numbering every line of your proof. The premises will come numbered, the conclusion is off to the side, and then you start numbering the next lines of your proof starting after the number of the last premise. So every line is numbered, and that simply so that you can refer back and say, I got this from line 2. And where you use a rule of inference, you label the rule of inference that you used, referring to it by the standard abbreviation, or let's just say an abbreviation that no one could fail to understand. So when you use simplification, and I suppose the standard abbreviation is SIMP, and you write SIM, no one's going to get lost. Good Lord, what was that? I thought you meant simplification. No, there's no such thing, and there's going to be no problem. You want to have clear, consistent use of the rules of inference, of some abbreviations for the rules of inference. This is, again, so that you can remind yourself of why an argument works, and so that you can communicate with someone else, like you can tell me, how you showed that the conclusion follows from the premises. This is a place just to repeat something I said at the beginning. And I don't mean this to be a grand claim about creativity, intuition, insight, and logic, or anything like that. Just to be a statement about the mechanics of inferential proof, by contrast with the practice of truth tables to demonstrate validity. As you recall, when you map an argument out on a truth table, you look for what we call a counterexample. You ask yourself, will there be any lines in that truth table in which all the premises are true, but the conclusion is false? One such line or more shows you that you have a counterexample, that is to say that it's possible for all the premises to be true and the conclusion false. You can't have that in a valid argument. Therefore, you have shown that the argument is invalid. In the absence of any such lines in your truth table, right, where there are no counterexamples, you know there are no counterexamples, then you know that the argument is valid. Now, things are a little different with proof by rules of inference. Clearly, if you start with premises and you apply rules of inference, and they're legitimate rules, legitimately applied, and you arrive at the conclusion, you have shown that the argument is valid. You have shown that from these premises, this conclusion follows. Okay, that's why it's called a proof. And what we were talking about last week in the metalogic digression, what's called the soundness of truth functional logic, assures you that when you are following the rules of inference, and you start with the premises and you reach the conclusion, so that you've played the game right, you've won the little game of this proof, you've walked from the premises in your way to the conclusion, that answer you arrived at is reliable. The argument really is valid. The inference really does work, okay? But suppose you don't. Suppose you start with the premises and you do your best, because I know you're going to do your best, but you do your best, and no matter how you apply those rules of inference, you just can't seem to wind up with the conclusion. What follows? Well, of course, maybe the argument is invalid, right? It doesn't work. Or maybe the argument's perfectly valid and you simply have not seen how to prove its validity. I'm sorry to tell you this. You can't tell which it is. That is, you cannot tell from failing to arrive at a conclusion whether that failure is your failure alone or an indication of the invalidity of the argument. Okay, that's in practice the biggest the biggest disadvantage to working by rules of inference by comparison with the truth table. It's not a machine, as I said at the beginning of today's session. You can't, it's not an algorithm. You can't promise that you'll arrive at the conclusion. Now, it would be a little bit mean if at this stage in studying logic, I were to throw a lot of invalid arguments at you just to get you frustrated and always unsure whether the argument really were invalid or there was just something wrong with your reasoning process. So you can assume that the arguments you deal with at this stage are valid arguments, and you simply need to use the right rules of inference in the right order, applied to the right lines to get to those conclusions. Okay, there's no point in as it were building a maze that you can't get through to the other side. But we still have the very pragmatic question: how do you proceed? How do you know which way to start to get from the premises to the conclusion? Well, as we go over some of these examples in class together, I'll point to tips that sometimes help. The book contains other tips that sometimes help, rules of thumb, rules of the road. But in general, I would say this: if you start along a certain path and then it becomes clear that that path is not going to bring you by your walk to the conclusion, you can always scratch it out and start over and take a different path, right? No harm is done. That doesn't have to feel like a failure. Realizing that one strategy doesn't work just means you haven't yet shown that the argument is valid. Okay, I hate to mix metaphors here. The other metaphor I would appeal to is those of you who drive cars, and if you've ever had to drive long distances on unlit roads at night, you might know the rule of driving: don't try to see past your headlights. You know, you've got a certain area that is covered, is illuminated by your headlights. You can see within that area. Follow the rules of inference as they lead you within the illuminated area. If you don't know yet what's going to happen beyond the reach of that illuminated area, don't worry. You'll get to it and you'll see. If it doesn't work, you can always start again. This isn't a race. Now let's just have one little example and see what we can do with it. Suppose we start with these three premises. If A, then B, not C or A, not B, and not D. And we want to conclude not C. All right. One rule, and I like the way your textbook distinguishes between top-down and bottom-up approaches. You don't always have to keep the difference between those two in mind. But in general, sometimes you start with the premises and see where you can go. That's my favorite approach, just to be honest with you. Yes, you can look at the conclusion and think, okay, I'm going to have to get this from there, right? But I prefer just to walk right into the thicket of the premises, say, well, this follows and this follows, and then maybe from there I can see how to get to the conclusion. In any case, one thing you can notice, one thing you can look for, is not what propositions seem particularly germane or relevant to the conclusion you seek, But on the contrary, what propositions seem completely irrelevant, extraneous, they don't belong there at all. You might want to think that's a clue that those are the letters you want to get rid of, okay? If there's a way to get rid of them. Now, in this case, you see that there's A, B's, and C's all over the place. A C is in the conclusion, so you better not ignore the C's in the premises. And the A's and B's appear more than once. But then you have little old d. Look at little old d here. It's not going to wind up doing any work at all. Maybe the person who wrote the proof just threw that in to confuse you. Well, is there any solution? Well, when it's a conjunction, the solution is easy. Remember that rule, simplification. A conjunction gives you two or more propositions. You're always welcome to eliminate one of them and just keep the one you want. So what would happen here in premise 3 if we deduced the negation of B alone? Right? That's from line 3 using simplification, not B. Well, not B is also not in the conclusion. The only other place you can see it, indeed, is in premise 1. Aha. But you've already gone over and over these rules of inference enough to have them tattooed on your brain, okay? Not B, and if A, then B, you know that you can get the negation of A from 1 and 4 by modus tollens. Now, again, we're just looking around. We've got a not A in our hand, and we're wondering, can we apply it somewhere? Well, we can't apply it to premise 1. After all, that's where we got it. We can't apply it to premise 3 because there's no A there. But in premise 2, we see a disjunction, and the disjunction has an A as one of the disjuncts. Now you've got the negation of A. That means, which rule is that? That's right, disjunctive syllogism. By disjunctive syllogism, if a disjunction tells you it's one or the other, and you know it's not one of them, it's got to be, yes, the other. So from not C or A and not A, you can infer not C. So that's from lines 2 and 5 by the disjunctive syllogism. Now, I was going to go a step further because I was a little absent-minded and I was carrying out this proof, when suddenly I realized, well, that's the conclusion we were looking for, the negation of C. It's a short proof. Well, but it was a constructed proof. It was made so that it would have a solution. Yes, but I think you can say that about a lot of the arguments you're going to be dealing with in this course. They're made so that they can be solved, okay? Again, they're constructed so that you can have a valid inference, and you can take that valid inference, and your challenge is not to determine whether or not the argument is valid, for you may often presume that it is valid. The challenge to you is to show how one can start with the premises and, in the metaphor of the toddler trying to walk, get across the room to the conclusion. That's all we did just now. We started with the premises, applied a few rules, and before we knew it, we had the conclusion in hand. Beyond this, the rest is just practice, doing lots of examples, seeing which rules of inference apply, and labeling them and getting your way to the conclusion you want. That's all for now.